seconds away. It's,
Hi, everyone. So before we start the group session today, so it looks like there was some confusion about question 1 from the assignment on deriving EM for the Bernoulli mixture model. So I thought I would go through it here. So what we did for the question, since there was enough confusion, we decided to give everyone full credit for their assignment solutions, but hopefully we can make the we can hopefully get everyone to understand and fix their solutions for the group submission. So there's a good chance to kind of get a second try at this question. So what I'm going to do is I'm going to go over the solution here, and then we're going to have our normal group session. So just a reminder what this problem is. So this is the mixture of Bernoulli's model. So that is, we have a z variable, which we index by n, and that, and depending on z, we get a bunch of x variables, x, n, j, x, I should say xn1, xn2, all the way up to xnd. So we asked you first to come up with the Q function. By the way, I think there's a little bit of confusion about the use of this terminology, evidence lower bound. That's something you see often in variational inference. The evidence lower bound is also can be used to describe the Q function. There's a close relationship between variational inference and EM. I'm hoping we will get a chance to cover variational inference. That's scheduled for the last week of our content. So depending on how quickly we go through everything else, I'm hoping we can get to it. But so there's a close relationship between EM and variational inference, and in both cases, you're ending up with this lower bound on the evidence, which is why you'll see the same terminology used. But we're talking about the Q function for EM that we've defined all through this week. So we want to define the Q function and then derive both the E-step and the M-step. So I'm just going to go through and we're going to do the solution here. So okay, so first question is to define the Q function. So we have Q, which is a function of theta and all the QNs, equals, this is just coming right out of the textbook here, sum over n okay, by the way, so there's some questions about this expectation notation. In general, an expectation, we talked about this in the Canvas, but in general, expectation of some function f of x, this is just the definition of expectation, is sum over x of p of x, f of x. Usually we don't have to write any subscript here because which distribution we mean, p of x, is implied. In the case of EM, I think it's helpful to do so. So in EM, we're specifically assuming that Zn is distributed according to these particular distributions, Yn. Okay, and the question asks you to simplify, so let's simplify. Sum over n, keeping that. We're going to write out our expectation. So to do our expectation, we need to sum over the possible values of z of n. Those values are k equals 1 to d, because this is a mixture of k possibilities for z of n. Of our mixture probability, q of n of k, times log of this density here, or this probability here, which is, we have two parts to the probability, because again, we have the model that looks like z is the parent of x. So this is pi k times product, just got a parentheses going here, product j equals 1 to d mu k j x n j 1 minus mu k j 1 minus x n j. So this here, this part is just our Bernoulli probability that we've seen a bunch of times before. And then this part is our cluster probability. So this comes from our categorical distribution over the different clusters. Okay, and we can simplify a bit more, so let's do that. This thing, by the way, we gave it another name, specifically in the case of mixture models. We call this RNK. Let's write that a little nicer. RNK. Just two names for the same thing. We're going to use that. So here we get sum over n sum over k. I'm not going to bother putting a subscript r and k. Now our log is going to split things up here. We're going to get log pi k plus sum over j x and j log mu kj plus dot 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 this thing here. I'm just going to say for the sake of time, I'm not going to write it out. Log of the top times log of the bottom. Okay, so that's our Q function. Good, so that was part one. Please, if there are any questions, oh, it looks like there are. Will this be posted on YouTube lectures? Yes. Should the outer sum be from K to big K? So let's look at the problem definition. Yes, thank you. Oh, outer sum. Thank you. Yes, you're right. This guy. My mistake. And yeah, please do stop me if there are any questions. And I got this one right? This one, good. Okay. Okay, so that's question one. Let's go to question two. So question two, let's go back to the problem statement. We want the cluster responsibility RIK. And okay, I thought we fixed this in the assignment, so sorry about that. So we're mixing notation here. Apologies for this. We're using I and N interchangeably. We used N in the lecture, and we've been using I in the assignment. So sorry for that. You'll see both notations used often in kind of the literature. We've been using N in the lecture, like I said. I we're using here, and then notice we used an N here that should have been an I to match our I here. So sorry about that. So and then because I'm used to the lecture, I'm using N in my definitions here. So in general, you should try to be consistent. We will try to be consistent in the future. We would give you full points if you mix up N and I in your solution. Okay, so we want the M step. The M step is going to be very similar to the case of a Gaussian mixture model. So this is our E step. Let's write that out. We need to do probability of Zn given K. Oops. Equals K given X theta. Okay, so this is going to look very similar. By the way, in general, this is very close to the Gaussian mixture model example. We're going to do the same thing we've done a lot of times in this course, which is just use Bayes' rule. So this equals probability of Zn times probability of Xn given Cn. I'm dropping the dependence on theta here just for the sake of notation, but all these are given theta divided by sum Zn prime of the same thing as above, but with Zn prime. Equally, we could have used, and actually, let's just be explicit with this notation. This is Zn equals K here. A more explicit way to write this would be Zn equals K prime. Okay, so that's our Bayes rule. We can write it out more. We can write out exactly what we mean here. So what is probability of Zn? That is just pi nj. What is probability of Xn given Zn? sum j equals 1 to d. Oops, should be product. Mu k j to the x and j 1 minus mu k j to the 1 minus x and j over same thing, but sum k equals 1 to k prime rather. Okay, and then this thing is the same. Okay, so that's just our Bayes rule. Hopefully that's very familiar to everyone. Okay, so last step is we need our M step. So we need to take the derivative of our Q function and set it to 0. So let's do that. Partial derivative of Q with respect to mu kj equals, well, let's simplify a bit. This is going to partial derivative of the following thing, again, with respect to mu kj. A bunch of these terms are going to go away. Okay, so we're going to get, so first thing, we're going to keep our sum over n. So let's keep that here, sum over n. Notice that only one of our, there's a sum over k, but only one of those sums, or only one of the terms in the sum is going to have a k matching the one we're taking the derivative of. So we can get rid of that sum. We have our r and k. Here, let's do something better. I'm going to underline all the terms that we keep. Keep this one, we keep this one, we can get rid of this one. And then this term, notice, doesn't have mu kj in it. So we're going to get rid of that one. We have a sum over j, but only one of those j's matches the one we're looking for. So this thing is going to be just x and j log mu kj plus, again, this thing over here. Okay, so we just have to take the derivative of this thing. At this point, it's just a bunch of algebra, so I'm not going to continue doing this here. Notice that, so I think we've done this before. We've done EM for Bernoulli, our Bernoulli distribution. And notice that this term is exactly the same as, or I guess that's part of the expression, is the same as for normal mixture model. The only thing that's new is this thing. So it's pretty easy to see that when we, if we do, so we'll take the derivative, we'll set it to 0, we'll do a bunch of algebra, and we'll end up with this thing here, which, by the way, looks very similar to our normal Bernoulli MLE, which is sum xij over n. Okay, then it also asks you to do the math estimate. That's also looking very similar to our other math estimates. We're going to end up in our Q function. We're going to get another term that's not going to have have the sum in it, of course, because this is just our prior term. So there's going to be something here. That thing is going to be the following. By the way, let me check for questions here. Does the screen change? I'm not sure what you mean by the screen. And question 2 is, am I writing on the screen? Yes, I'm writing on the screen. Hopefully everyone can see my writing. Hopefully people have been, would be complaining earlier if you hadn't seen my writing, because all I'm doing is writing on the screen. So if anyone else can't see my writing, please let me know. Can we think of this problem as randomly selecting one of k bags, each with d coins in them, and each coin when flipped follows our Bernoulli distribution? Yes, that's exactly right. So The only trick with that is that there would be labeled coins. So maybe we have 5 bags. Each one has 3 coins in them: a red coin, a blue coin, and a green coin. And the way we generate this data is we randomly pick a bag with some probability. We flip the coins, and then we get red coin either heads or tails, blue coin heads or tails, green coin heads or tails. And the probability of heads and tails of the red, green, and blue coin might change from bag to bag. Okay, and just to finish this up, okay, we have our prior, which is going to give us a term that looks something like alpha plus 1, alpha minus 1. Log mu k j plus beta minus 1 mu 1 minus u k j. So by the way, I don't think we've defined the term conjugate prior in this course. A conjugate prior is one that has this nice property where you'll notice when you do the math that the alpha just gets added to our sum of xnj's, and beta gets added to our sum 1 minus xnj's. And so alpha minus 1 and beta minus 1 end up being kind of pseudo counts. So it's conjugate in the sense that we keep our closed form of solution, and everything looks very similar once we add the prior. But anyway, we didn't have to define that term to see that all the math carries through. So, and again, I'm not going to go through all the algebra, but we just get these extra terms here added to our sum. Okay, let's see if there are any more questions here. Okay, hopefully that helps everyone. So now I'm going to close this, and I'm going to open the rooms, and we can have our normal group session. Okay, so please join your appropriate group.